In the process of building your most awesome model ever, you will work with a number of different intermediary models and settings of those models. Here is how to evaluate these models so that you can compare their performances. The first thing you need to do is to design your learning process in such a way that the final model's performance can be estimated. And you can only do that based on a part of the dataset you have. But for the error estimation to be a good approximation of the error on unseen data, the model has to be estimated on a part of the dataset that is never used in the training phase. And so this leads to the idea of splitting your dataset into two. On one hand, you have a training dataset, and on the other hand, you have a test dataset. And you experiment with different models, different hyperparameters, different learning algorithms on the training dataset, and you only use the test dataset once as an estimation of your final model. There are some popular choices that people use for this train test split. Here are some of the most popular choices: 80-20%, 85-15%, 90 to 10%. But these are just rules of thumb. You can also split, and indeed in many applications they are split with different percentages. And one aspect you have to take into account when you think about the optimal split for your dataset is the size of the dataset. And you've got to remember that the purpose of the test dataset is to be large enough to be statistically significant. And for a very large dataset, even smaller percentages than those that I have on this slide will be enough, because they will give you a large enough test dataset. So this should not be taken as a strict rule. These are just popular choices that many machine learning scientists apply in practice. One aspect of this train test split is that you might have in your dataset and in your application, you might have categorical data. And these different categories, very often they will be unbalanced. In other words, you will have categories that dominate the other ones. You will have much more data in some of the categories than you have in the other ones. And that's problematic, because if you train with a split that's not carefully done, for example, you train with a split that never sees this particular category, then obviously the learner will never have a chance to learn anything about this category. So it will be wrong for any data point that you will test on later on coming from this category. So the point here is that you would like to have this sort of stratified data split, meaning that when you take a sample, for example, you separate the testing data set, you will want to take this sample roughly proportional to the data distribution you have in your original data set. So in our case here, you have about 1/4, 1/4, 1/2. And you will aim in your sample to have roughly about the same distribution as much as you can. The other point I want to make, and this is especially significant in medical application, is this idea of having grouped splits. And what this means is that some of these data points you will want to group together and have the whole group either just in train or just in test. To give you an example about this, you might have that you have data coming from individual patients. And so, for example, this could be what I indicate with numbers here. This could be patient number 3, and this could be patient number 5, and patient number 9, and so on. And the point is that if you send part of the data of these patients to train and part of it to test, you have an expectation that coming from the same patient, there will be a degree of correlation. And so in that sense, the testing phase will not be completely independent of the training phase. And so your estimation of the real error might be erroneous. So the point here is that you want to have a grouped split, meaning that whenever you identify dependencies in your data, which give you groups, for example, patients, as in a medical domain, those groups should be selected as a whole, either for the train or for the test, but never split a group between train and test. And this is obviously not relevant for all applications, but in some applications, you have this sort of grouped data, and that also has to be taken into account in the splitting data splitting phase. And then the point is, I replicate here the popular choices for split between train and test. But the point is that in the process of building your, ultimate model, you will have to go through a number of experimentations, comparisons. You will take different architectures, different sets of hyperparameters, and you will have to compare between them to see which one performs better, and then you iterate on that. You search even more hyperparameters for that one. And so there is this iteration where in the process of optimizing your model, you will need to test the performance of that model on some data set. And obviously you don't want to do that on the test data set. This is really to be kept just for the very, very final step, and you only use it once. You cannot really use it as an iterative procedure towards optimizing your model. And so you will need, something else, and this is where the validation, the idea of a validation set comes in. And for example, if you deal with a deep layer model, this validation set will be ideal to choose, for example, the number of layers, to experiment with models with different numbers of layers and check, which one seems to work better for your data set. Also to choose the number of neurons per layer. If you want to use a convolutional neural network, the number of kernels, the shape of kernels in each layer. You can experiment with different activation functions. You can experiment with different learning rates and so on, different batch sizes or different batch algorithms. And so the idea of checking the performance of each of these models is that you will have to do it on a separate data set than the training data set, and also separate from this test data set. And so the idea is that you will have to do another split of your training data set into something that's going to be kept just for training and something that's going to be kept for the validation phase. And again, validation phase is part of the overall training, but each architecture that you are testing or you are experimenting with is going to be trained just on the training data set, and its performance is going to be checked on the validation data set. And for these popular choices, the way, again, these are not, fixed rules, but very often you will have a split into 60-20-20, you will have a split into 70-15, 15%, and you will also have a split between train, validation, and test of 80-10-10. And again, for different data sets, maybe you have such a huge data set that you can afford even smaller percentages, or on the contrary, your data set is much smaller, and then even 20% for test data, for the testing data, is not going to be enough, and then you have to do something else, maybe go for 60-40, and then worry later about how to do this validation part. Speaking of that, if you have a small data set, indeed this splitting into train, validation, test is very problematic, because it's going to give you two small sets for validation and for test to get statistically significant results. And in this case, we can use a different concept. We can train a model repeatedly on different parts of the training data set and validate on the remaining parts of the training data set. And if we do this systematically, then we can increase the robustness of the results and the statistical significance of the error reported by the model on all of these trainings. And this is what's called cross-validation. So here is an example I have on this slide. And in this picture, you see the most commonly used form of the cross-validation technique. This is the KFold Crossvalidation. So what this means is that we will have k iterations, and in each iteration we will have a different validation set. And so, for example, here this will be our validation set, and this the whole thing here is going to be our training data. In this iteration we will have this particular validation set, and this part in here is going to be our training data, and so on. And the point is that, again, in this each iteration you have a different validation set, and together these validation sets, they cover the entire training data set. So we have a sort of a sliding window concept to select the validation set in each iteration. And in particular, what this means is that each data point will be selected in the validation set in one of the iterations and in the training data set in k-1 iterations. And a typical choice for k is 10, but again, this is not a fixed rule. It depends a lot on the size of the dataset and on the application. The point being here that the validation set has to be large enough. And all the other considerations on stratified sampling and on grouped sampling will still apply in this case. You will have to do this sort of splitting here in the k-folds in such a way that you follow the principle of stratified sampling or the group sampling if that's what you need in your application. So, I mean, we are going to train k different learners based on the machine learning model that we are experimenting with, one learner for each one of those folds in the KFold cross-validation. So the difference between these learners is that each one of them is going to be trained on a slightly different the training data set, and its performance is going to be evaluated on a different validation set. And we are going to collect each model's error on its own validation set, and then we combine them, remembering that each data point is exactly in one of those validation sets. And so this overall error that we get out of all of these k learners is going to be the overall error of the, it's going to be the KFold cross-validation error of the model that we are working with. Again, you have here an example in this figure how this goes in terms of splitting between train and test for a model that only has 12 data points, and we do a threefold cross-validation. And one point I want to make is that the higher k is, the more robust the learning part is going to be. But on the other hand, also the higher k is, the smaller the validation sets are going to become, and so their error is going to be more difficult to estimate with confidence. And there is, of course, also the problem, the cost of training more models with higher k. For larger data sets, the number of folds can be smaller, and the point here is that in this case the training sets are large enough, so you need less iterations. Here is another option for cross-validation. This is called the leave one out cross-validation. And here the point is that when you do your k folds, in fact, k is going to be exactly equal to the number of points in your training data set, and you will have in each iteration exactly one data point in the validation data set and all the other ones in the training data set. So you will have, for all of these n different learners that you are going to train, you will have in the validation set exactly one data point, different from learner to learner, and in the training data set exactly n-1, all the other ones except the one that was selected for validation. Again, you see here this example where we have 8 data points, and doing this sort of leave one out cross validation is going to give us 8 different combinations of learners, and we will have to train all of them and then combine their error like we discussed for the KFold cross validation. There are also other, perhaps less popular options, but it's good to know about them. All kinds of different exhaustive cross-validation, where we split the train set into train and validation in all possible ways. But there is also this idea of leave p out cross-validation, where the point is that you will choose an arbitrary natural number p, and then you will say, in each fold of the cross-validation, I'm going to leave out exactly p data points. and you are going to do all possible combinations of these P data points. So depending on how big this P is, you are going to have the number of different learners that have to be trained grow quite quickly. So in that sense, this is something that should be dealt with a lot of care. Here is another idea for estimating the performance of your learners, and that is bootstrapping. And this is an alternative to cross-validation. And the idea is that you are going to generate your training sets through sampling with replacement. And so the idea is that we are going to sample endpoints with replacement, meaning that we sampled it, but there is a chance to select this point once again at a later point. So in some sense we select it, but we put it back into the set, into the data set, sort of speaking. And so we sample n data points from the original data set that has size n. And of course, I mean, because it's done with replacement, some of these data points may be selected several times and others, not at all. And those that are not selected form the validation set, and those that were selected form the training data set. And so that gives you the split, train, test, and again you are going to do this a number of times to gain statistical significance, and you are going to train different learners for each one of these combinations, and check overall what's the estimated error for this model. And I would like to reason with you about the typical size, the expected size of the trained dataset in bootstrapping. And here are a few points to make about this. So if I'm thinking about several probabilities, so the probability of, so on one hand, the probability of selecting a point. So you have your favorite point, and you are asking what's the probability that this point is going to be selected in the next sampling, and that's going to be obviously 1 over n. I mean, all of the points have equal probability to be selected, and the probability of not selecting a point is obviously 1 minus 1 over n, and then the probability of not selecting a point in n consecutive draws. So that's going to be obvious because these draws are independent of each other. So that's going to be obviously 1 minus 1 over n to the power n. And the point here is that as you have n growing, to infinity, as you have very large data sets, so this is going to go as n grows. This is going to approach e to power minus 1, so 1 over e. And 1 over e is about, 0.368. So the point is that the typical size of the validation data set, or the expected size of the validation set, is going to be this 36.8% of the original data set. And so by, the other part, the typical size of the trained data set in bootstrapping is going to be 63.2% of the original data set.